We'll start with today will be these waves. Now, waves is something that you've seen or experienced for that matter. Yeah. I talk to you, waves are produced. You throw some stones in a pond, you see those ripples. There are some waves that you can't see, some of them you can see. You can't see the waves, you can see the displacement of water. Or how many of you play any musical instrument? The morning batch had a bit more. The hands go up now. Which one? Most common? I know on the campus most common is the guitar. So, you've ever tuned the guitar, somebody? No? Yeah. What do you have to do? You change the fret and then how do you match this frequency on the string? I bow my head. Well, no. For a more novice like me, what would I do?
Press the key on the keyboard.
Press the key on the keyboard, right. And if I assume that my keyboard is not giving me the correct frequency, buy a tuner. Now, what that tuner is, essentially you've done this experiment again. When you tighten, we take one of the strings, you keep on tightening it. There's a paper rider kept on top of the string. Has everybody done this in school? Yes. Yeah. You have this, and then you take a tongue. That's the tuner. Yeah? A pair of tongs, hit it on a rubber thing, starts to oscillate, bring it close to the wire, and the paper rider flies away. So the same thing with the guitar. Yeah? That's how you essentially tune the guitar. Now, I don't know if you've actually done this experiment, that if you had taken this paper rider and put it on the first string, the lowermost string, it would fly off if I had a tuner with the same frequency, of course. If I had put it on the sixth string, it would fly off again. Why? They're both? Same notes. Same notes, but are they both the same frequency? No? So how many octaves high is it? Just two? This is first octave, this is second, it's in the third. So 2 octaves high. Okay, so if I were to think of the wavelength of the uppermost string, then let me say that these are the two fixed ends of my guitar, and that's the wavelength of the, okay, so that's half the wavelength of the uppermost string. What would be the wavelength of the lowermost string in that case? As you said, it's 2 octaves high.
1/4 of the wavelength of the.
A fourth? A third?
1/4.
Why fourth? You said 2 octaves high.
It's 2 octaves higher. So if it's 1 octave higher, it will be half. So if it's 2 octaves higher, it will be 1/4.
Good. So your wavelength in that case would have zeros here. It would, the wave would fit like this. So either the wave fits lambda by 2 or lambda, and somewhere in between I'm sure you will find the one in the second octave as well, which would, as you said, if there was something in the second octave, that fellow would be twice the wavelength or half the wavelength, right? Half the wavelength of the green one. So something of that sort. I don't know if there are any more, but yeah, sure, there should be another one at least, another E note on your guitar, at least one more. But what you notice is that I can fit in these two ends either a wavelength of lambda by 2, right, or a wavelength of 2 lambda by 2, or a wavelength of 3 lambda by 2, or 4 lambda by 2. So lambda by 2, 2 lambda by 2, I think instead of this being 4 times, it should have been 3 times. Huh? 4 lambda by 2. So these are the kind of things. So essentially what I can fit in is n times lambda by 2 to make a standing wave over there. Yes? This n being an integer. Yes? These are the only waves that I can generate if I pluck a string that is separated by this particular distance. Now what I have done is the example I gave you was of 2 or 3 different strings, but I could actually, what I did was I placed the paper writer on the topmost string, which has the green wave function, so as to say, but I put a frequency of the bottommost string, which is more like the red one. Okay, and still I could allow the paperclip to fly, which means that there's some resonance between this and that, which means that even the higher string has some component of the higher frequency wave vibration, right? So the higher string, whose normal mode is the green one, also has overtones to it. The first overtone, which would be the yellow one, the second overtone, which I have not shown here, the third overtone, which would be the red one, and so on and so forth. So what we are going to discuss today is essentially how these things come about, because that maths which we develop today will be required for going on to quantum mechanics. So let me start with that. So it's a very simple problem, and as I told you, and you know, you've studied electromagnetism, so you know that the wave equation of some wave which is, let's say, fixed on these two ends, so that's x equals 0, that x equals L, and then I have some wave, and that's my mean displacement position, and let's say that's my amplitude u, which is a function of x, of course, if you think of the wave going anywhere, right? It's a function of x, the displacement, the mean displacement from your 0 line. And if you think of the guitar, then it's going up and down. It's also a function of time. And the wave equation that you've already learned is equal to 1 by v square del square u by del t square. And I won't go and derive this again because that took you about 6 months in your school. All the Maxwell relations coming back from electromagnetism, bringing them together, electricity and magnetism, and then getting these wave equations. It took you a lot of time, right? No. अब तो जेई के लिए पढ़ लिया, आप किसको याद है? So we start from here. That's your classical wave equation. V is the velocity, the wave velocity, and u is a function of both space and time. And we are just looking into this one-dimensional wave, right? So it's only along this string. A two-dimensional wave would be the one on tabla, right? That would be on these 2 dimensions. How this tabla, the entire, what do you call this? Membrane of the tabla would go up and down, right? So, and we have something called boundary conditions. The boundary conditions from the figure are obvious. It is that my strings are fixed at x equals 0 and x equals L. So my boundary conditions are that u of x, so let me take x equals 0 at any given time t should be equal to 0, and the other one is that at L at any given time t should be equal to 0. Right. Now, as you saw in thermodynamics, that I could make any function of two variables, right? And why I could do that is because I could vary those variables independently. So that's why I could write that du is equal to del u del v times dt plus del u del v times dv plus del u del p times dt, right? So I could independently see the change in volume, so change of the internal energy as a function of volume and as a function of temperature, because I could vary these two variables independently. Like that, x and t can be varied independently, and if they can be varied independently, I can always write u, which is a function of x and t, as a multiplication of a function of x and a function of t. That's the most general form. I mean, the function of t could be something, the function of x could be something, we could have some additive terms there, some device, something that could divide. So multiplication is the most general form we could write. Now, if I do that and plug this capital X and capital T into my equation, the left hand side is just a derivative, a second derivative of x. So what I get is t comes out to be a constant for that, and then I have an ordinary differential, not a partial differential, because I am just doing it for a function of small x, and the right hand side comes out to be d square, what happened? D square t by dt square. Okay. I could do a slight rearrangement of these variables and get 1 by x of x, d square x of x by dx square is equal to t, no,